So if you're back, it's because you wanted to either do number 2 with me or check your number 2. This is the part from the textbook that tells you what's going on, what they're going to ask you for. They're asking you for the local linearization equation, and they're asking you for how accurate that approximation is. When it says see comparisons following example 1, that's going to show you how we were doing the same thing in notes to report our error or difference between our model from our linearization and the actual. So in order to do this, we're really thinking we're modeling it by writing the tangent equation. So at A is -4 is that center of linearization that they're asking us for. So in order to find the tangent equation, which is the linearization equation moved around a little bit, we have to find out, well, what happens at -4 for this function so that we can actually find the tangent equation there. So at -4, that function becomes the square root of 16 plus 9. So at -4, the function's actual value is 5. So that's the center of our linearity. We're interested in the function's slope at that point, so we need first derivative. First derivative of our function is going to be 1/2 times that quantity, times the quantity, no square root. I'm going to actually put it into exponential form to the -1/2 power. Chain rule, derivative of the inside. Clean up our derivative just a little bit. The half and the 2 cancel, and my derivative becomes x over the square root of x squared plus 9. The reason I need derivative is that's going to be my slope at -4 for my tangent line. So I'd be looking at -4 in the numerator, and I already know that the denominator becomes 5 for the -4 value. So I'm looking at a slope of -4/5. So if you're in the writing this like a tangent equation and moving it around mode, here would be my tangent equation. Adding that 5 onto both sides, it becomes my linearity model. I can change that y to L of x. We're saying we're using this to model the behavior of the function really near the ordered pair -4, 5. So this would be our answer to part A. There's our linearization of that function at an A of -4. Part B wants to know how accurate that comparison would be 1/10 away from the center. So we would run our linearization at -4 plus 0.1. So we'd be running our linearization equation at -3.9. And at -3.9, that's going to be 5 minus 4/5 -3.9 plus 4. So basically it's calculating the difference between those two. And if you check that, we're going to get 4.92. Then you need the actual function's value at -3.9. Your calculator's good for getting that. Subtract that 4.92 that we found. Don't worry whether it's positive or negative, we're only considering the distance between the two. And the number you get, you don't need to write this down unless this helps you decide your error. Okay. And then there's a bunch more values. We notice that the first time we see a change or that there's a difference between these two numbers is in the 4th decimal place past the 0. So our answer would be that our error is less than 10 to the -3rd, because at 10 to the -3rd we do not have a difference between the two values yet.